Hello everyone and welcome to Reinforcement Learning Tutorials. This is the second part of the tutorial on the Deep Q learning networks. In the first part of this tutorial, we presented the basics of the Deep Q learning networks. In the second part of the tutorial, we will explain how to implement the Deep Q learning networks in Python, TensorFlow, and OpenAI Gym. As you can observe over here, we are testing the Deep Q learning algorithm in the Cart-Pole OpenAI Gym environment. As you can clearly observe, the Deep Q learning algorithm is able to keep the pole in the vertical position. And this is done by continuously applying actions, that is, forces to the cart. And the forces can be push the cart right or push the cart left. Without Deep Q learning algorithm, this pole will simply collapse and the episode will be finished. So after watching this video and studying the Python code, you will be able to generate this amazing simulation and you will be able to impress your coworkers, your colleagues, or your professor. To implement the Deep Q network learning algorithm, I'm using the object-oriented approach. I defined a class called Deep Q Learning that implements the algorithm, and here is the class. In the sequel, we explain the main components of this class. First, let us start with the init function or the init method. This function accepts as inputs our environment. In our case, this is the Cart-Pole environment, gamma parameter, this is the discount rate, epsilon is the parameter for the greedy approach, this is basically a probability for exploring the environment, and the number of episodes is the number that denotes the number of simulations or trainings of the learning algorithm. After initializing these variables, we define additional variables. These variables are state dimension. To remind you, the state vector consists of 4 entries. These entries are cart position, cart velocity, pole angle of rotation, and pole angular velocity. We have 2 actions, and that's why the variable action dimension is equal to 2. The actions are push the cart right, and that's the action 1, and push the cart left, and that's the action 0. Here is the replay buffer size, and it's equal to 30. To remind you, the replay buffer stores all the tuples that have this form given over here. So in every cell we have a tuple, and the tuple consists of current state, current action in the state S11, reward obtained by transitioning from the state S11 to the next state S12. S12 is the 4th entry of the tuple, that's the next state, and isTerminal is a Boolean variable denoting if the terminal state or if the next state is the terminal state. By saying that the replay buffer dimension is 300, we are saying that we can store 300 of tuples. Next, we define batch replay buffer size. Basically, we train the network by randomly sampling tuples from the replay buffer. And we form another data set or another batch of data, and this batch of data is used for network training. And the dimension of this batch of data is 100. That is, we store 100 of tuples. The next variable is update target network period. This means that every 100 steps we update the parameters of the target network. That is, every 100 steps we copy the parameters from the online network to the target network. This is a counter used to update the network, the target network better to say, and we initialize it to 0. This list stores sum of rewards obtained during each training episode. This list is used to track the convergence of the algorithm. Here, we basically initialize the replay buffer as Q data structure, we set the maximal size, and this is a very important step. Next, we create the network. As you will see later on, we call this function create network, and this function will be defined in a SQL. Then we define the target network by creating a neural network, and the target network and the online network have the same structure. Then at the beginning, we basically copy the weights from the online network, or the main network, how it's called in this code, to our target network. And then finally, we defined an empty list of actions, and this list of actions is used to define the cost function, as you will see later on. And that was our init function. Next, we define a function that creates the network. And here is the definition. We are using the standard TensorFlow approach for defining neural networks. We specify that the model over here is a sequential model. This means that we add layers on top of each other. Then we add the first layer. It's a dense layer with 128 neurons. The input dimension is the state dimension. And as activation function, we use ReLU function. This is the second layer of the network. Again, it's a dense layer. Activation is ReLU again. And the third layer is the output layer. We use a dense layer, and the dimension of this layer is equal to action dimension. That is, it's equal to 2. And this is the output of our network. And the activation is linear. So let us explain this structure over here graphically. Now, if you watch the first part of this video tutorial, you will remember the graph that you can see over here. And this is basically the structure of our network. This is the input, it's the state vector, and the network maps the state vector into two outputs. The outputs are action value functions for the corresponding actions. Here the action is equal to 0, and here the action is equal to 1. And this is exactly what we define in our code. Next, we compile the model. We use the optimizer RMS prop, and it's very important here to keep in mind that we define a custom cost function. And this is the name of the cost function that I will explain later. And as the metrics, we use accuracy. And finally, we return the model. Next, we define the custom loss function over here. And it's very important to properly understand this loss function. Basically, we want to implement the cost function that you can see over here. However, the main issue is that these two objects, or better to say matrices, are not exactly yi and this prediction over here. These matrices that are provided as an input to this function have a different structure. And this structure is basically determined by calling the fit function. And the structure is determined by internal TensorFlow functions and some other things that I don't have enough time to talk about in this video. So let me explain you how to go from these two vectors to our cost function. The function has two inputs. The first input is y true and the second input is y predicted. So let us illustrate them. This is basically y true and this is y predicted. Y true has this structure and y predicted has this structure. Its dimension is equal to dimension of our sampled replay buffer. That is the dimension of batch replay buffer size, and keep in mind this is not the original replay buffer dimension, this is the dimension of the sampled replay buffer. So over here we will have, let's say, 100 entries, since we specify the size of the sampled replay buffer to be equal to 100, and we will have two columns, column 0 and column 1. Here also we will have for y predicted column 0 and column 1. Now, it's very important to keep in mind that only certain entries of this matrix will correspond to the actual values of yi that are defined over here. And this is our target. So only certain entries are actually used for optimization. The remaining entries, for example, the entries given over here, are not used for optimization. So we don't need this entry, we don't need this entry, we don't need this entry, we don't need this entry. On the other hand, y predicted is basically a prediction performed by the neural network. And again, we have two columns, and the predictions correspond to QS action 0 and QS action 1. And these are the predictions for different states. That is, the rows correspond to predictions for certain states. So what we need to do, we need to match this value with the value over here, and to use these two values to form the cost function. Similarly, in the second row, we will need to match the entry over here with the corresponding entry given, for example, over here. And we will use this entry and this entry to form the cost function. The choice of proper entries is actually encoded in one vector that we defined in the init function, or better to say, a list. And this list is called actions append. So if this action append has a series of entries, for example 0, 1, 0, 0, 1, 0, etc., and this list is updated during the training process, we will select corresponding rows and columns of this matrix. So for example, in this case, since we are seeing 0 here, this means that we will select this entry over here. However, I didn't define it very well, so I need to change over here the first entry to be 1, since I specified that the first column should be selected. So I will change these two entries over here, erase this since this is not important, and now everything is fine. So if here is 1, this means that we need to select this entry over here and this entry over here. And these two entries are actually then plugged in something like this to define the first part of the cost function. That is the first part in the sum of the cost function. And then we again look into this actions append list, and if we find 0 as the second entry, we go back, we take in the second column, for example, this entry over here and this entry over here to form the cost function. That is to form the second sum in the cost function. And we repeat this procedure. So going back to our customly defined cost function, we basically perform these steps. Here we extract the indices. Here we extract from the list actions append proper columns that need to be used in order to form the cost function. And here we use basically the TensorFlow function mean squared error to define the cost function. And we finally return the loss. Next, we define the function for training the DeepQ network learning algorithm. And here is the function. We loop through the training episodes, then we initialize the rewards obtained in one episode as an empty list, and this list will store all the rewards obtained during each episode. Then we reset the environment. This means that we start from a random initial condition. For example, we start from a condition that can look like this. And you should keep in mind that all the entries of the state vector, x, x dot, theta, and theta dot, are selected to be in the interval minus 0.05 to 0.05. So every training episode starts from a random initial condition. You should also keep in mind that this function, environment.reset, returns the current state. That is, it returns the initial state. Then we set terminal state to false, since the next state is obviously not the terminal state, and we loop through the time steps of a single episode. This loop will end when this flag becomes equal to true, that is, when the next state becomes equal to the terminal state. Here, in the particular state, that is in the current state, we select an action. For example, going back to our diagram, if this is our state, we select an action, A, by using a proper policy. And over here, we are basically using the epsilon greedy policy. And I will explain this function select action in the sequel. Here, you should just keep in mind that the function select action takes as an input current state and takes an index of an episode because the actions are determined on the basis of the current index. Then we apply the action, that is, we step. So we call the OpenAI Gym function step. What happens over here? Once we apply the action A, our environment will evolve to the next state. For example, the state over here. And the pole will rotate and the cart will move. So this is the state S, and this is the next state, let's say S prime. The function step returns the next state, returns the reward, and returns this Boolean flag that denotes if the next state is a terminal state. Because we are currently in the first step, the terminal state will not be reached, so this will be false probably. Then we append the reward to the rewards list. Then what do we do over here? We create a tuple and we append this tuple to the replay buffer. So what do we do over here? Initially, the replay buffer is completely empty, and we basically form a tuple, and tuple is S, action, reward. Reward is obtained by transitioning from the state S to the state S prime, and then we have this Boolean flag is terminal. And this is appended to our replay buffer, the big replay buffer that has dimension 300. Then what happens next? We train the network. Now, as you will see later on, since the replay buffer is completely empty, we don't train the network. We wait until the replay buffer is full, that is, until 300 steps are passed, and you should keep in mind that steps can span several episodes, so we don't do anything over here, since in this function, train network, there is an if statement saying if the replay buffer is not completely full, don't do anything, just return. And what do we do next? We set the current state to be equal to the next state, and we go at the beginning. At the beginning, again, we repeat the whole procedure. Now the state S is not anymore S, it's S prime. Then in the S prime, we select actions and we proceed further. We repeat this procedure. This while loop is looped until the terminal state is reached. That is, when S prime becomes the terminal state. Then the loop is broken and the first episode is finished. Then again we go back to this for loop, index of episode is now 1, and we start with the second episode and we repeat this procedure. Now, we need to explain two things. We need to explain the function select action, and we need to explain the train network function. Let us first explain the select action function. Here is the select action function. It takes as an input the current state and an index of an episode. Here you can put this conditional statement saying if an index is larger than certain number, for example, you can specify this number equal to 10, then you simply return random actions. So you completely explore the environment if the index of the episode is, let's say, smaller than 10. This means that during the first 10 episodes, you completely explore the environment. You don't care about the optimal strategy. However, I keep the index here smaller than 1, since I don't want to randomly explore my environment. Next, we implement the epsilon greedy approach. We randomly sample a number. This is a number from 0 to 1. So let us explain that. The number is called random number. So we will have a random number sampled from the interval 0 to 1. Now, if this number is smaller than epsilon, we randomly choose control action. So we randomly choose either a is equal to 0 or a is equal to 1, and we return the corresponding value of a. However, if the random number is larger than epsilon, we don't randomly select the actions, we use the greedy approach for selecting the actions. The greedy approach is very simple. We basically use a neural network to predict the action value functions for the given state. So we set state, use the online network or the main network, and we obtained two values. We obtain q as a is equal to 0 and q as a is equal to a. A is equal to 1, better to say. Now, we select the greedy actions, that is, we select an action corresponding to the larger value of q. For example, let us say that this value is 0.7 and that this value is 0.8. Since 0.8 is larger than 0.7, we select action a is equal to 1 and we return this action. And that's the main idea of the epsilon greedy approach. So you can see how the epsilon greedy approach is implemented. For the time being, forget about this if statement. Over here, we return a random action, that is, if the random number is smaller than epsilon, and epsilon is usually a tolerance, can be a number from 0 to 1. Usually I select it as 0.1 or 0.2. Otherwise, we perform greedy actions and we return the greedy actions. And that's it. Now, there is one small detail here. Over here, I'm basically saying that after 200 episodes, I will gradually decrease the value of epsilon. So I'm doing this in order to explore less in future episodes. That is, let's say in episode 1000, I want to explore less compared to the episode 100. That's why I will slowly decrease the epsilon. I'm doing this because I'm more and more confident as the time goes by that my actions computed on the greedy strategy are more optimal. And that's the trick. And finally, let us explain the function for training the network. The first step that we need to check is the following. We need to check if the replay buffer is empty or not. That is, if we still have some space in the replay buffer, then we don't perform training. That is, we simply skip the training process and wait until the replay buffer is completely full. If the replay buffer is completely full, we proceed. Over here, we sample the data or the tuples from the replay buffer. Graphically, we are doing a step that's shown over here. This is our original replay buffer. It has data spanning across several episodes, and we randomly pick up tuples and we form this data batch that you can see over here, that sample batch of tuples for training. Next, we basically form the training data sets that are fed through the neural network. We basically enumerate the random sample batch, the sampled batch, and then we perform appropriate steps in order to extract the states, the current states, and the next states. Next, we use the target network to predict the Q values. We simply place to the target network S prime, that is next states, and this is basically a batch of the next states extracted from the random sample batch, and we provide to the online network, that is to the main network, input current state batch consisting of the batch of the current states, and we obtain the predictions. So these are the action values predicted by the target network and the online or the main network. Next, we form the batches from training. We basically take these two matrices and we reshuffle them and we form appropriate matrices on the basis of these matrices, and the steps are pretty much straightforward and they are given over here. Basically here we loop through the entries of the random sample batch and we form the data for defining the cost function. Basically, we form y entries given over here or given over here. So we need to test if the next state is a terminal state or not. On the basis of that, we define yi, and over here we append the proper actions that correspond to proper states in order to define the cost function. And then we define the output of the network and we simply call the fit function providing the output of the network. We specify the batch size and we specify some other parameters. We use 100 epochs for training the network. You can use more epochs or a smaller number. However, I found that 100 is a relatively good number. So this function will go to the customly defined cost function that's given over here, and it will perform proper mathematical operation. It will choose the proper entries from its inputs, that is from here and over here, and form the cost function that you can see over here. Next, we need to check if the condition for updating the target network is satisfied. In every step of training, we update the counter. This counter counts how many time steps has passed in between update of the target network. And if this counter is larger than this pre-specified number, update target network period, let us see this variable at the beginning of our code. It's equal to 100, so this means that every 100 steps we update the target network. So if this condition is satisfied, we simply copy the weights from the main network to the target network and we update the target network. You can choose this number to be equal to 300, 400. However, in this particular case, I discovered that 100 is a relatively good number. And at the end of this if statement, we reset the counter for updating the target network. And that's it. That's basically the class for implementing the deep Q learning network. Next, I explain the driver code that explains how to use this class. In my particular case, I saved the class in the file called functions final, and I saved it in this folder over here. Now, I basically created a new file called the driver code final, and this file is also saved in the same folder. And make sure that your folder is active over here. First, I import the class. From functions final, that is from the name of the file in which you defined your class, I import DeepQ Learning. Then I import the gym environment. Instead of gym, you can also use gymnasium, and gymnasium is a version of gym that's being actively maintained. I heard the rumors that gym is not maintained anymore. However, I'm not 100% convinced that this is the case. However, I also tested the code on gymnasium environment and it works perfectly. Next, I create my environment. Then I select the parameters. Gamma is equal to 1, discount rate, epsilon is 0.1, epsilon is the epsilon parameter for exploration in the epsilon greedy algorithm, and here I set the number of episodes to be 1000. However, my advice is to increase the number of episodes to be 5,000, 10,000. However, it will take you a significant amount of time to train the network. In my case, it took me at least a day to train the network such that I get relatively good results. Then I create an object, and here's the object. Then I'll run the learning process, and here I will not run the learning process since, again, it takes a very long time to learn the network. However, I have a remedy for that, and I will provide you a remedy for that I will explain in the sequel. After the learning process is completed, you can basically retrieve the sum of rewards, and you can summarize the model later on. Now, what I do usually when I train my model, I usually save the model parameters. So here I have a file called train model temp h5, and this is the trained model. So if you want to quickly test the performance of the Q learning method, that is the deep Q network learning, I will provide you this file, and this file is posted on my GitHub page, and all the links are provided in the description below this video. So you can simply load this model to test the performance of the Q learning algorithm. So how to load the model and to test its performance? I created another file that simulates the training model, and here's the file. It's called simulate trained model, and as I mentioned, it's available on GitHub. So what do I do over here? I import Keras, I import the class, DeepQ Learning, I import gym environment, I import NumPy, and over here I load the model. And while loading the model, it's very important to properly specify the custom cost function. Otherwise, basically, the load process will not produce the proper model. So you need to specify the cost function. And here you specify where this cost function is defined. It's defined in the class deepqlearning, and the name of the cost function is myLoss function. So this is a very important step. Here I test the sum of obtained rewards, then I create an environment, and I reset the environment. Now, you can also create a movie if you want by uncommenting these two code lines. For example, you can comment this code line to create a movie, or you can also uncomment this code line to create a movie. However, I'm not going to create a movie right now. However, you still have that option. And here I simulate my optimal learn policy from the saved model. So let's see how this thing works in practice. I will simply execute this, and I will run the code, and you can see here, so these are the basically prediction time steps, and here's the simulation. And this is exactly the simulation from the beginning of this video. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.